So my project is the investigation into the feasibility of a piezoelectric-based micro-force sensor for minimally invasive surgical robot tooltip. It's a bit of a mouthful, but it will become clear later on in the presentation. My supervisors were Dr. Hadi Sadati and Dr. Christos Bergley. Now, currently, complex multi-step procedures such as optic nerve sheath fenestration can't be performed by a robotic system entirely. This is because the state-of-the-art in surgical robotic systems like the Da Vinci system does not have any force sensing capabilities. An optic nerve sheath fenestration, as shown in the figure, is used to treat raised intracranial pressure. If left untreated, it can cause blindness, but because eye tissue is so delicate and the procedure so complex, the risk of blinding tissue damage is very high. So the procedure is a last resort. Even slight imprecise force application in vitreoretinal surgery can cause blindness. Now, the forces required in optic nerve sheath fenestration microsurgeries are in the range of 0 to 0.5 newtons to puncture the optic nerve, as shown in this figure from Mitros et al. And a study by Gupta et al. Found that approximately 75% of the forces during minimally invasive retinal microsurgery were below 7.5 millinewtons, and only 19% of these forces can be perceived by the surgeon's phalanges, their fingers. This force resolution required far exceeds human fingertips resolution. Not only that, but if surgeons apply inadvertent force from hand tremor, poor kinesthetic feedback, patient movement, or surgeon fatigue when performing traditional microsurgeries, they could cause fatal tissue damage. Hence the requirement for force quantification in minimally invasive microsurgeries. So the state-of-the-art in robotic force sensing is lacking greatly. The state-of-the-art is the Da Vinci. This system doesn't offer any force sensing capabilities, although it does offer some proprioception. Haptic feedback is lacking. The main obstacle introducing force sensing is cost, as if the sensor cannot be sterilized in an autoclave, it will become disposable, hence making the cost a lot higher. And without the capability to palpate different tissue types, the surgeon cannot palpate and differentiate between healthy and unhealthy tissues, and cannot apply precise forces required in minimally invasive microsurgeries. So possible force sensing methods considered were DC motor current demand. This is where the current demanded by each motor at the robotic joints is proportional to the forces applied to the robot. But this introduces noise in the signal from inertia of the robot and friction at the joints. Strain gauges were also considered as a solution, resistive-based sensing. A flexure that changes resistance when deformed, and if the stiffness is known, then the force applied can be determined. But strain gauges suffer from hysteresis and do not give repeatable results, as well as complications that come with autoclave sterilization of electronic systems and miniaturization of the strain gauge. However, the force sensing method investigated was piezoelectric based. So the solution investigated was a 0.4 mm diameter piezoelectric line tension sensor called Piezola. This could be wrapped helically or placed concentrically within a CTR, a concentric tube robot. This can then determine the bending force as a piezola experiences torsion when helically wrapped and the nitinol tubing is bent. The response to bending, torsion, contact, both static, quasi-static, and dynamic forces was investigated. And to explain the workings of the sensor, first I'll quickly explain the piezoelectric principle. As shown in the diagram, when a centrosymmetric crystalline piezoelectric structure is deformed, the average position of charge is moved. And this is a potential difference across the material. And the deformation is therefore proportional to the potential difference, and force can be determined with the elastic constant of the material through Hooke's law, F is equal to Kx. Now, to test the response of the piezola to different deformations, we tested the dynamic torsion, quasi-static torsion, quasi-static tension, and dynamic tension. Quasi-static being a force that is changing in time but very slowly, so it can be considered static. So the dynamic torsion testing rig is shown here. CAD designed and 3D printed test rig and signal amplification system that has an operational amplifier circuit, a National Instruments data acquisition unit. The 3D printed clamps with a linear stage with a resolution of 10 micrometers, a stepper motor that was run at different angular velocities and different angular displacements, driven by an Arduino with G-code. This was to determine the signal response to the different angular velocities and different angular displacements. We also tested the quasi-static tension to determine the signal response with a precision linear stage and CAD designed 3D printed clamps. All experiments were conducted on a vibration isolation optical platform, so to minimize the noise input from the surroundings to the Piezola. The quasi-static torsional rig is shown here, constructed in a similar way to the others, CAD 3D printed mountings with precision rotational stage and precision linear stage for pre-tensioning. The right image shows the experiments to determine the elastic constant of the Piezola, so to map displacement to force through Hooke's law. The response as a contact force sensor was also investigated when placed concentrically within nitinol tubing. This was to act as an analog to a concentric tube robot. A concentric tube robot being a continuum robot that consists of nitinol tubing that's placed concentrically, where the stiffest tube governs the coarse movements and the least stiff governs the fine control. So each tube can be translated to give a high degree of freedom. And the Piezola was tested for its response to a torsional force as a helically wrapped sensor arrangement around a nitinol CTR was considered. As if the CTR experiences bending, then the Piezola would then experience torsion, thus the bending force can be quantified. One interesting finding when placing the Piezola within nitinol tubing was that it was very sensitive as a contact force sensor. From this we garnered that the Piezola's response to static charges on surfaces needs to be investigated further, as the response to body tissue and body fluid static charges would be relevant as an in vivo robotic minimally invasive force sensor. Now, the signal acquisition method was a National Instruments DAC with an inverting operational amplifier. In the video shown, the torsional responses of the Piezola is determined. I'm sending G-code to the stepper motor via an Arduino microcontroller. As you can see, the signal for different displacements and different angular velocities is then acquired through National Instruments DAC Express. And then I exported the data graphed and interpolated in MATLAB to show the angular velocity and angular displacement relation to signal. The results are shown here. This shows a clear relationship between an angular velocity and angular displacement relation to signal. This would benefit from more data to smooth out the curve. It was also determined that the Piezola was insensitive to non-time varying forces such as quasi-static tension and torsion, although this was to be expected considering the piezoelectric principle. Furthermore, the Piezola picked up literal noise acting as a microphone, so sensitivity to vibration needs to be investigated further. Possible application of that would be a sensor to detect the resonant frequency of tissue when an ultrasonic pulse is emitted, thus determining the stiffness of the tissue. So, in conclusion, deskilling minimally invasive robotic surgery by introducing force sensing capabilities would allow otherwise complex multi-step procedures such as optic nerve sheath fenestration to be performed, as they are a last resort otherwise. And minimizing the risk of tissue damage would improve the health-related quality of life and the recovery time of the patient, as well as reducing surgical robotics training costs, as Riley et al. Found that the introduction of force quantification in surgical robotics training reduced the learning curve. And that would allow for better allocation of resources in value-based healthcare. An interesting application would be contact-free intraluminal navigation for thrombectomy, as well as vitreoretinal surgery. Now, the main limitations of the Piezola are that it's insensitive to quasi-static and static forces, and it's also sensitive to static charges on surfaces, which is relevant for in vivo sensing. So to be in production, the sensor has to be cheap enough to be disposable, or robust enough to be in an autoclave for sterilization, as well as high precision with little calibration needed. So future work would entail investigation into the response of static charges on surfaces, relevant for in vivo sensing, as the sensor would meet body tissue and body fluid. So thank you for listening. I'm continuing this project and publishing in the MDPI Micro Machine Special Issue, Soft Robotics, Materials, Systems and Operations, with the help of Dr. Hadi Sadati, Zikong Wu, and Dr. Christos Berglis. So thank you very much. Here's a quick video of the Nitinol concentric tube robot analog acting as a contact force sensor with a Piezola placed concentrically within.